particular FTP. So first of all, am I audible properly? Am I audible?
Yes, sir. No problem in that.
Yes,
Okay.
sir. Audible.
So, considering the fact that you people are from diverse fields, I am from core chemical engineering background. So, this presentation which I have made is specifically I have designed it in such a manner so that even field from all field of engineering people can just understand this. So, I have taken the concept from chemical engineering. I have taken concept from mechanical engineering, some concepts also. Basically, I have been working in the field of fuel cells for a period of last 15 years. Initially, my main focus is on solid oxide fuel cells. So therefore, my presentation reads as solid oxide fuel cells, the future source of power and heat generation. So my presentation will consist of many components in which I have discussed general fuel cells rather than solely solid oxide fuel cell. I have taken this title because my research area was solid oxide fuel cells. So for that reason, I took this particular topic, that is solid oxide fuel cell as a future source of power and heat generation. Right. So first of all, so the current scenario of the energy supply. So if we presently look into the scenario of energy supply, so we are presently based upon the combustion of fossil fuels as our major resource of energy. And you all know that fossil fuels, they lead to a lot of problems. They lead to a lot of environmental problems like pollution, acid gas emissions. There is emission of greenhouse gases also, that is depleting the ozone layer. So if we consider the present scenario, what is there is that there is a ever increasing demand for energy. So the main demand for the energy, if we look into today's scenario, is based upon the supply of electricity for various purposes, for industrial purposes, for residential purposes, and the second thing is the transport of goods and persons. So considering the current ever increasing per capita energy consumption in the world, what we need is the utilization of advanced and efficient energy systems. And second thing is, most important is we have to keep our environment clean. So considering that factor, this is a fuel cell is a very good parameter that is there, that can be adopted for keeping these two things in mind. So if we just see the future fuels and electricity, so I have just classified into two categories. One is now. So now we are using fossil fuels, that is natural gas, petroleum, coal. We are using steam turbines. We are using some combined cycle involving steam turbines. So at the limited usage now and the future, because many of these energy sectors which I have just told here, they are presently being utilized to some extent. Research is going on for commercializing these particular areas. So for limited usage and future, we have nuclear energy, solar energy, renewables. Of course, a lot of renewables are being discussed, like wind energy is a renewable energy. That's what I discussed in the morning. So we have a distributed generation system, superconducting transmission lines, and other future fuel that can be used. Then we have hydrogen from fossil fuels and water. Super grid is another concept that is a transmitted grid over a wide area. The electricity can be supplied in a proper fashion. So my topic, fuel cells and new processes. So we will be talking about this particular topic that is fuel cells and new processes. So what are the key drivers for fuel cell technology? So the key drivers, first is an increasing energy supply to meet the growing demand. So the energy required, that is increasing, particularly in developed countries. The amount of energy, per capita energy is increasing at very fast pace. So we have to increase the amount of energy supply so as to meet the growing energy demand. Second thing is that reducing reliance on imports. So we have certain countries are having an upper hand of the oil, and we have to rely on imports for meeting our energy demands. So that reduction is required for that oil imports, and for that matter we need fuel cell technology. Then of course a very important parameter nowadays, that is environmental quality. So for improving environmental quality we need greenhouse gas emissions, the reduction of that, and meeting air emission regulations. What are the regulations that are given by the various pollution control boards? So that norms has to be met. So for that very reason we have this key drivers for the fuel cell technology. These are the key drivers. Then what exactly is a fuel cell? So Just a straightaway definition is a electrochemical device that directly converts the chemical energy from a reaction between fuel and oxygen into electrical energy. Okay. So what we have? We have a chemical energy that is stored in a fuel, and that chemical energy of the fuel in the fuel cell, that is with a reaction with oxygen, it produces electrical energy that can be used. And of course, the only byproduct is water. There is no combustion of fossil fuels that is involved. So that is the main thing that is from an environmental point of view, this is very acceptable a fuel cell. So then, why fuels are the emerging energy source? So we have just the chemical energy of the fuel that by reaction with an oxidant or oxygen, it produces water, it produces DC electricity. Of course, if we need like AC electricity, that DC electricity can be conditioned to form AC electricity. So then when I talk about an electrochemical device that converts the chemical energy stored in the fuel into electrical energy, another device that comes into mind is the battery. So what is a battery? Battery is a similar device. It also converts the chemicals into electricity. But the battery, you very well know, you use a battery in your car, you use a battery in your Activa or so, and that battery, after long usage, it becomes dead and you have to throw it away or you have to recharge it periodically, right? So that is finished in the fuel cell. Fuel cell never go dead. The electricity flows out as long as the chemicals, they constantly flow into the fuel cell. So last is that fuel cells are very attractive from an environmental point of view for the generation of electricity, because there is no combustion of fuels, so there is no carbon dioxide or other pollutants that are produced. So just simple, I have two diagrams here just showing how fuel cells generate electricity. We have the diagram at the left that shows basically a fuel cell stack. So fuel cell stack is composed of a number of fuel cells connected in series of parallel arrangement. So that fuel cell stack consists of an anode and electrolyte cathode. We will come to that. The fuel, that is hydrogen, is fed to the anode. The oxygen is fed to the cathode. So they react to form water and they generate electricity. So besides this, a fuel cell stack, we have another thing that is required for today's scenario is that we don't use hydrogen as a fuel. So we can have another fuel that can be processed to form hydrogen. So in the second diagram on the right, it shows here that the fuel can be fed to a fuel processing unit which generates hydrogen, and that hydrogen can be fed along with air to the fuel cell stack, where the reaction occurs to form steam and DC power is produced, which can be conditioned to AC power, right? So this is the different type of fuel cells that are commercially available. That are there. I've just given just a slide showing the comparison and types of the different fuel cells. So we have first is the electrolyte. First is the molten carbonate fuel cell, MCFCs. Second is the phosphoric acid fuel cells, and then I have polymer electrolyte membrane fuel cells, and the last is our solid oxide fuel cells. Right. So in this particular slide which I have given here, the operating temperature is given. The operating temperature is minimum for the polymer electrolyte membrane fuel cell. It is of course maximum for MCFCs and SFCs, that is molten carbonate fuel cells and solid oxide fuel cells. So reforming is a process. Basically, a second parameter I discussed is reforming. So reforming is basically conversion of hydrogen based fuel into like methane into hydrogen. So that reforming can be external or it can be internal. So it is normally external reforming for phosphoric acid fuel cell and polymer electrolyte membrane fuel cells. But for SFCs and for MCFCs, it is reforming is external or it can be internal. So efficiency, if we just consider efficiency is maximum for the case of MCFCs and SFCs, that is 45 to 60%. If we talk about efficiency with cogeneration, when I say cogeneration, that is basically besides the generation of the electrical energy, we are utilizing the waste heat also of the fuel. So that is maximum energy with cogeneration. So that can be up to 85% for SFCs and MCFCs. That is much greater as compared to phosphoric acid and polymer electrolyte membrane fuel cells. So the power output ranges is given. Waste heat can be used for space heating for our fuels, or it can be used for generation of steam, for driving a turbine, for secondary power also. So then this is just slide again shows the various type of fuel cells. It just shows their operating temperature, what is the fuel that is fed, what are the products that is formed. So solid oxide fuel cells and MCFCs, that is molten carbonate fuel cells, they work directly with hydrocarbon fuels. So that is that rather than pure hydrogen, we can use hydrocarbon fuels. So typical the power generation is around 200 plus kilowatt power residential units can be used. So we have phosphoric acid fuel cells that is mainly used for combined heat and power. So polymer electrolyte membrane fuel cells presently, if I just consider, they are presently used for transportation purposes. So of course there has been research going on for shifting this to solid oxide fuel cells. Alkaline fuel cells, they are mainly used for space shuttle like Apollo program. So they are using alkaline fuel cell. So then just an outlook of the applications that is there for the fuel cells. We have, it can be used for stationary power. Just come to detailed applications also. Stationary power, it can be for industrial purposes, it can be for residential purposes, it is vehicular power, it can even be used for portable electronics like laptop or cell phones. So then the next slide here shows the fuel cell applications in detail. So we can have micro power plants. So rather than having a centralized power plant supplying electricity to different homes, so we can have a micro power plant. So it is that basically removes our dependence on the electric grid distribution. That is, we have a house that is there in mountains and there is no as such supply of electricity there. So what we can need is just a fuel to the fed to a fuel cell, and we can have a remote standalone package for the generation of electricity there. So besides that, even heat can be also generated along with power, so that can be useful for hilly areas. Then even for commercial and industrial applications, fuel cells are of quite significance. They provide, the reason is that they provide clean, high efficient power for on-site grid support and grid backup and even grid independent electrical generation needs. So they can be used as a backup support, or they can be used as such complete for system for supplying power, right? So even with military applications where we need uninterrupted power supply system, so we can go in for fuel cells. So I'm talking about general fuel cells. So I will just come to a slide that is which fuel cells are used for which applications. Then in communications, which involve a high priority carrier. So for that matter also, where we need high grade power. So corporate and government sectors, they are relying on fuel cells applications. Right. So this now slide shows the various applications and the various fuel cells that are employed. Of course, their sizes and their the traditional fuel that is employed for using them is also shown here. So power system and power electronics, so they require quite sufficient small size power. So we can use polymer electrolyte membrane fuel cells, MCFCs and SOFCs. The fuel that is for PMFCs is pure hydrogen. MCFCs and SOFCs, they can even use methanol as a fuel. Then for micro combined heat and power generation, so we have PEMFCs, again polymer electrolyte membrane fuel cells, and SOFCs. So the fuel that can be used as LPG, or it can be natural gas, or even LPG can be also be used for SOFCs. So for auxiliary power units, we use normally SOFCs. For distributed combined heat and power, we use all type of fuel cells. That is polymer electrolyte membrane can also be used. MCFCs, SOFCs can be used. So predominant fuel that is used is natural gas for that matter. So for city buses, we use till now polymer electrolyte membrane fuel cells. I told that this polymer electrolyte membrane fuel cells are mainly used for vehicular pollution right now. So of course the shift has been going towards solid oxide fuel cells in very recent times. So for large power units, we can use SOFCs with gas turbine systems, and the fuel that is used is most commonly is natural gas. So now, why SOFCs over other fuel cells? So SOFCs are one such of type of fuel cells which have, I told, there is an anode, there is an electrolyte, and there is a cathode. So SOFC is one such type of fuel cell which has all the components in the solid state. That is, even the electrolyte that is used is not the liquid state, that is also a solid electrolyte. So that is one distinct advantage of SOFCs over other fuel cells. So for that very reason, it has even no corrosion problem because the electrolyte is not a liquid, so there is no corrosion problem. Even there is no leakage occurs because the electrolyte is a solid. So the other advantage is that the only byproduct that is produced in SOFCs is water. So we can have off gases from other fuel cells which may be even harmful to some extent. So they are quite inexpensive. I will just come to the slide involving what are the material of construction of SOFCs. Then we will come to that. They can be quite inexpensive, right? So then last thing is that they don't require an external reformer. Reformer is because the SOFCs, they operate at high temperature. So for high operation temperature, the methane or any other hydrocarbon fuel can be reformed in the fuel cell itself. That is referred to as on-board reforming of fuel. So on-board reforming of the fuel can occur forming hydrogen, which actually is a fuel for the SOFC. So there is no pre-reformer, I would say, rather required for SOFC. That is also one distinct advantage of SOFCs. Right. So another slide showing a comparison of various type of fuel cells. So if you have a liquid fuel and upon evaporation, that liquid fuels can directly be used in solid oxide fuel cells and MCFCs. Why? Because they operate at high temperature, right? And if for natural gas, we have to first remove the sulfur content of the gas before feeding to SOFCs and MCFCs. So SOFCs and MCFCs, they have a thermally integrated reformer. That is because of their high operation temperature. So the forming takes place within the fuel cell itself. So as we go down, that is if we come to the phosphoric acid fuel cell. So phosphoric acid fuel cell, the first thing is we have to convert the fuel into hydrogen. Methane cannot be used as such in the fuel. And the carbon dioxide concentration fed to the phosphoric acid fuel cell should be less than 5%. So then for last, that is polymer electrode membrane fuel cells, they are the fuel cells which require pure hydrogen as a fuel. And for that matter, the carbon monoxide concentration should be less than 10 ppm. So if we just go down the series, here we have an increasing complexity of the fuel processing. And of course, the decreasing efficiency. I have just shown the efficiency before. So efficiency of SOFCs and MCFCs are greater, right? And further, it requires the other fuel cells. They require a lot of fuel processing before being fed to the system. So then let's come to the SOFCs, the principle of operation. Just see this diagram here. The principle of operation is very clear to you. I will just briefly tell you that we have an anode. That is of course a solid material. We have an electrolyte, that is also solid material. Cathode is there. So hydrogen as a fuel is fed to the anode, and we have oxygen that is fed, air is fed at the cathode. So the oxygen of the air that gets reduced at the cathode and it forms oxide ions. The oxide ions, they pass through the permeable electrolyte. They reach the hydrogen, there they react with hydrogen, with ions, oxide ions, it forms water and electrons. So the electrons, they move from the external circuit. So this external circuit movement of electrons, that is basically conventional current moving in the opposite direction, right? So what we have basically is that the characteristic of the material is such that the electrolyte is an ionic conductor. It allows oxygen ions to pass through them, but it does not allow the electrons to pass through them. So that is the characteristic of the materials that has to be chosen for SOFC. Then only it will actually generate electricity, right? And the excess fuel and the water that is just removed from here. So the unused gases are removed on the cathode side also. So now this I told that hydrogen, it reacts with oxide ions at TPB. There is written oxide ions migrate through the permeable electrolyte to reach the TPB. So what is exactly TPB? That is I'm going to explain in this particular slide. So what is TPB? TPB is a triple phase boundary. So triple phase boundary is where the electrochemical cell reaction occurs. So the electrochemical cell reaction is occurs at the triple phase boundary. So the triple phase boundary it involves the coexistence of the electrolyte. The electrolyte is there. The electron conducting metal phase is there. That is basically anodic material. and the gas phase. So these three phases together, just shown on the left slide here. So these three phases together, they are referred to as triple. So I'm very sorry for the interruption that occurred. Actually, there was a network issue that was there. So I will just take a brief. I will just review the concept I've just discussed before, so that the concept becomes clear to you. So I was talking about SOFCs as the system for generation of electricity. So what is the principle of operation of SOFC? So SOFC, it consists of a porous anode, that is a negative electrode, a porous cathode, that is a positive electrode. There is a electrolyte, that is the dense oxygen ion connecting one. So the fuel, that is hydrogen, is fed to the anode, the oxygen air, that is fed to the cathode, and the oxygen from the air that basically gains electrons from the external circuit. It forms oxide ions. So this oxide ions, they pass through the electrolyte, permeable electrolyte, react with hydrogen to form water. And when they form water, so the electrons that are generated, that move into external circuit. So this external circuit movement of electrons leads to conventional electric current in the opposite direction, right? So there is a TPB, that is the triple phase boundary, where this electrochemical cell reaction occurs, that is the reaction between hydrogen and oxygen to form water. So this TPB is because of the coexistence of the electrolyte, the electron conducting metal phase, and the gas phase that is required, right? So these are the various reactions that occurs in a natural gas fuel SOFC. Basic reactions are that oxygen reacts with electrons, they produce oxide ions. The oxide ions, they pass through the electrolyte, they reach the anode, and the hydrogen that reacts with these oxide ions to form water, and it produces electrons. These electrons move in the external circuit, leading to the generation of electricity. So the overall cell reaction can be just taken as hydrogen reacting with oxygen to form water, right? And if we have a natural gas fueled SOFC rather than having a hydrogen fueled SOFC, in that case we have methane basically as a fuel. So methane reacts with steam to produce hydrogen, which is the actual fuel for the SOFC. So the carbon monoxide that is generated, that reacts with the steam to produce hydrogen and again carbon dioxide, and this is the water gas shift reaction. We have a complete methane reforming reaction also. If in excess of steam, the methane reacts with steam to produce hydrogen and water, and this hydrogen is used as a fuel for the reaction before, that is the overall cell reaction for generation of the electric current, right? So these are the typical materials used for SOFCs. So anodic material, that the properties of the anodic material should be stable, it should be electronically conducting, it should be porous, and typically we use nickel on vitreous stabilized zirconia as a material for the anodic component. The cathodic material should have high electric conductivity and ionic conductivity. It should have catalytic activity for the reduction of oxygen, and should be again chemically and thermally stable, and it should be stable in the oxidizing atmosphere. So typically material that is used is lanthanum strontium magnetite, that is LSM layer is there. So electrolyte has a very good role to play in an SOFC. The electrolyte is a solid material, but it has a peculiar characteristic that it is an oxygen ion conductor, but it is an electron insulator. So because of this very characteristic, it is that the fuel cell actually generates electricity. So it is typically that material that is used for electrolyte is YSZ, that is vitreous stabilized zirconia. Then we have certain auxiliary materials. So sealing material is there for gas tightness. We need a glass ceramic for sealing the hydrogen from the oxygen so that they don't react with each other initially only. So interconnecting materials are there. So for connecting one of the cell, for producing a sizable amount of voltage, we have to have a number of a stack of cells. So these stack of cells can be connected with each other by means of interconnecting materials. So typically interconnecting materials that are used are doped lanthanum chromide has been used as an interconnecting material. So these are just the SEM images and TEM images of typical anodic material, the cathodic material, and the electrolyte. And electrolyte has been used normally used as YSZ. Of course, the donated oxygen has also been used. So interconnecting materials are either metallic or ceramic layer, and typically materials used are, it can be chromium iron based alloy that can be used as an interconnecting material. So these are the synthesis techniques for components of SOFCs. So there are solution combustion synthesis, co-precipitation method is there, hydrothermal synthesis is there, Folger process is there, spray pyrolysis, polymeric complexing method is there, reverse Buchla synthesis is there. So those who are interested in taking some synthesis as a system for fuel cell and research. So these are the various techniques that are traditionally being used. So polymeric complexing method and reverse Miller synthesis are the techniques that have been used very recently, right? So solution combustion synthesis I have used in my research work. I have generated nickel on cerium galbanate ceria by means of solution combustion synthesis. So in that case, normally we take nitrates of different materials, that is cerium nitrate, galbanate nitrate, and nickel nitrate, and we add a fuel into it. Glycine as a fuel we add into it, and upon combustion it produces nanoparticles which can be compressed to form, which can be pelleted to form a component, anodic component, or even electrolytic component of an SOFC. So now let's come to the major challenges that are there for SOFCs. So the major challenges that are there, that it should have good electrical conductivity. So of course that is the first and foremost. So then chemical and thermal stability of the component. So the component should be chemically and thermal stable, then only they can be used in the material, because they work at high temperature and thermal mismatch may lead to problems. So intermediate temperature high performance electrode. So recently there has been research on producing intermediate temperature electrodes rather than the high temperature system. So carbon monoxide should not rather act like a poison. So there should be carbon monoxide tolerant electrocatalysts. So thermal mismatch between the different components is also should not be there, right? And electrolyte, that is the foremost thing that is there. That should be a good ionic conductor, electron insulator. So low cost fabrication processes should be there, and some novel materials should also be tested for fuel cells that are cheap enough, right? So SOFC has a distinct attractive characteristics. It has high conversion efficiency. So normal conversion efficiency is 50%, employing natural gas as a fuel. But if we use some heat recovery techniques in which the waste heat can be used, the conversion efficiency can be increased up to 85%. So 85% increase in the 85% conversion efficiency can be achieved. It has a modular design, so it has no acoustical pollution. There is no sound that is produced during this generation of electricity. So that is one system that makes it useful for residential electrical purposes for distributed generation of electricity. So no chemical pollution is there, only that produces water. So it can use in onboard internal reforming. So this parameter is because of this high operation temperature. So onboard reforming of the hydrocarbons can be done. It is load flexible, and we just discussed that also. It allows ease of siting and permitting. So then other attractive characteristics are there, that some commonly available ceramic materials can be used. So no moving parts are there, and there is no corrosive liquid electrolytes are there. So it is very reliable, maintenance free. There is no pumps required, auxiliary pumps required for circulating the hot electrolyte. So it promotes distributed power generation. That is, rather than having a centralized power system, we can have a distributed power generation system at our homes. So that can use as a for electricity generation. Then automatic application, it can be used rapid load response. It provides. So for automatic application, it is mainly used for providing auxiliary power, not for main power system. So it has a fuel flexibility. So let's come to fuel flexibility. When I talk about fuel flexibility, I'll just talk about these gas species that are there. We have hydrogen, carbon monoxide, methane. So hydrogen is a fuel for all SOFCs, but carbon monoxide is the poison for this phosphoric acid fuel cell and for polymeric electrolyte membrane fuel cell. It is a fuel for SOFC and for NCFCs. Methane, if it is a fuel for SOFC, but methane is not a fuel for any other SOFC. Right? So it has a large amount of fuel flexibility. So carbon dioxide and water that is present, that can be act like a diluent. Then sulfur, of course, is a poison that is there for all type of fuel systems, right? So then let's come to the fueling SOFCs. So these are the various fuels, because it is a fuel flexible system. So various type of fuels can be used. So natural gas can be reformed to methane. Natural gas methane can be reformed to hydrogen, which can be used as a fuel. We can use even watered gas, that is referred to as propane and butane. So also as the fuel for SOFC, it has a large amount of advantages. There is high amount of hydrogen to carbon ratio. So greater the amount of hydrogen to carbon ratio, greater the amount of hydrogen that is produced, right? So it has low vapor pressure, and there is no need for pump for pumping this watered gas. Even methanol and ethanol have been used as fuel for intermediate temperature SOFCs. So there has been some research going on towards using higher hydrocarbons like petrol and diesel for internal reforming for SOFCs, but that is quite complex because they're higher hydrocarbons. So reforming them in the fuel cell itself, that becomes a problem, right? So renewable fuels like biogas, landfill gas, so that can be used, but again they have a problem that the sulfur content of these gases, they basically lead to it leads to poison. It acts like poison, and for that very reason, the sulfur content has to be removed before feeding it as a fuel to the SOFC. So even industrially produced fuels like dimethyl ether and ammonia can also be used, but these are used mainly for portable applications. And the disadvantage is that they are relatively expensive, and of course they are available in pure form. Then the gaseous fuel that is obtained from coal gasification can also be used for fuel for SOFC. So we have a fuel flexibility. A large amount of fuels can be used in SOFC. So now let us, when I'm talking about natural gas as a fuel for SOFC, basically we are using a fossil fuel only. Right. Of course, the environmental concerns, of course, permits the uses of natural gas as a fuel. So now, why to use some other ideas which we can use hydrogen from source other than natural gas, or I would say some fossil fuels. So these are the sources of hydrogen production that are there. Besides that, we have electrolysis of water that is cheap and abundant. We have thermochemical production that is there. Then we have even photoelectrolysis, that is basically sunlight can be used for generating hydrogen. So that process has some lower efficiency. It is normally 1 to 2% efficiency on the photoelectrolysis, which is referred to as. So some new techniques have been developed. So with these new techniques, the efficiency has gone up to 4.5%. So there is another process known as biophotolysis. So this biophotolysis, that basically leads to conversion of hydrogen as a fuel from algae. So that is also some new idea for hydrogen as a fuel. So now let us come to if we use hydrogen for storage. So we also store hydrogen for using a fuel cell. So we need compressed gas tanks. We need traditional cryogenic liquid hydrogen tanks. We can use metal hydrides, but metal hydrides, as Dr. Amit has said, that is still under discussion. So metal hydrides. So some hydrolysis reactions can be used for hydrogen storage. Even nanomaterial materials that can absorb hydrogen can also be used for fuel hydrogen as storage. So recently, some research work is there for developing a three-dimensional lattice of hollow cubes, that is by Jeff Long, that is just shown the diagram here. So that is basically incorporating metal organic framework MOFs, each capable of storing 8 hydrogen molecules inside it. So this research is there for hydrogen storage that can, if that has really become realistic, in that case our storage of hydrogen for fuel cell becomes a reality. So then limitations. So because it is a solid electrolyte, it cannot leak, but solid electrolyte can break. So that can cause a problem. So other problem is there, that is it has somewhat higher manufacturing cost because of we are using high operating temperature. So higher operating temperature decrease the longevity and the reliability. So increased material oxidation is there, and induced thermal stresses are there because of the high temperature is there. So then I have basically certain, we are using SOFCs mainly for stationary applications, like, so that is for mainly heavy, sluggish, and expensive and fragile materials. So SOFC right now has not been used much for mobile applications. So we have to go in for some mobile application for SOFCs also. So this is the thermodynamics of an SOFC. We have fuel that is fed to the SOFC. There is an oxidant that is fed to the SOFC, and it results in some amount of work that is generated in terms of electrical energy. There is amount of heat that is produced by the SOFC, and there is a flue gas and an exhausted oxidant that is there, right? So if you apply the laws of thermodynamics to it, so we would just say the first law of thermodynamics just says that amount of the heat plus the amount of reversible work is equal to delta H. So delta H is the enthalpy change. So all of you know that. So enthalpy change is basically the enthalpy change because of the flows term and the enthalpy change which is because of the reaction term. So then we have the second law of thermodynamics that basically says the entropy change for a closed process, that is 0. So if we apply that, we get for a reversible process this particular equation. So next come to the thermodynamic principle says that the maximum possible reversible work that can be withdrawn from an SFC, that is the gives the free energy change for the reaction. That is the maximum amount of work that can be withdrawn from an SFC. So that is delta HR minus T delta S, right? And if I talk of thermodynamic efficiency, that is the ratio of delta G by delta H. So if I just talk about this electrochemical cell reaction, hydrogen plus oxygen gives water. So delta G, that is the Gibbs free energy change for the reaction, is just the Gibbs energy for products minus that for the reactants. And similarly, now let's come to the basic reaction of the cathode and anode. Oxygen reacts with electron to form oxide ions, and oxide ions react with hydrogen to form water. Right. So if I just see from these two reactions here, the molar flow of electrons is twice the molar flow of hydrogen. Right. So the electric current, that is a linear function of the molar flow of electrons, right? So, and we have a term known as Faraday's constant. So Faraday's constant refer to the charge on 1 mole of electrons, right? So we have this as the charge E, that is minus delta GR by 2F. Okay. So I just here define an equation known as Nernst equation. Nernst equation is actually that is there for showing the basically working of a fuel cell. So that is based upon the reactant pressure, temperature, its concentration. So Nernst equation says that the Nernst potential that is developed by an SFC is the standard Nernst potential that is developed plus RT by NF. N is of course the number of electrons, F is the Faraday's constant, and P is the pressure, and X is the mole fractions for hydrogen, X hydrogen, X oxygen, and X water, right? So the SFC that generates some electrical energy, but there are certain irreversibilities in the system. So these irreversibilities are activation polarization, ohmic polarization, and concentration polarization. So these polarization, they lead to decrease in the voltage that is developed. So what is activation polarization? That results from the resistance of the reactions occurring on the electrodes. Ohmic polarization is because of the resistance of the electrons and the resistance of the ionic flow. And the concentration polarization, you all know that as the reaction occurs in a fuel cell, the concentration is going to change from point to point within the fuel cell. So because of the variation in concentration, there is a concentration polarization effect that basically leads to the decrease in the voltage that is produced. So the net voltage produced, that is given by E0 Tp, that is the Nernst potential minus the amount of ohmic polarization, the polarization losses. So it is the activation polarization loss, or the ohmic polarization loss, or the concentration polarization loss. So the electric power produced will be just the voltage, the E cell that is produced into the current, right? So there are two parameters that are there. One is the fuel utilization coefficient that determines the efficiency of a fuel cell system. That is basically the ratio of the amount of fuel that is actually utilized to the amount of fuel that is fed, right? So XH2 inlet minus XH2 outlet by XH2 inlet. So we also define fuel cell efficiency by this particular relationship. So then those who are interested in modeling and simulation, yes, I am audible, right? So those who are interested in some okay, fine. So those who are interested in some modeling and simulation principles of SFC, which I have also done some research work regarding modeling and simulation. So there are some governing transport equations. So basically there are two things in an SFC. One is the flow channels through which the fuel flows and the oxygen flows, or the air flows, I would say. And second is the electrodes. So electrodes are porous in nature. So there are basically, if I talk about transport equations, there are 4 transport equations for flow channels. We have the conservation of mass, the conservation of momentum, the species balance equation, and the energy equation that is present for the flow channels that is just given in this particular slide. So we have for the porous electrolyte electrodes, we have basically two equations. One is the species balance equation and second is the energy conservation. So if we just see in this equation, there is a small parameter E. So that basically refers to the porosity. Because it is a porous region, of course, these equations will be dependent upon what is the porosity of this particular material, right? So let's now come to the flow of heat. The heat, because these are solid materials, there is flow of heat by conduction. The flow channels, there is heat flow of heat by convection, and because of the reactions and because of its high temperature, there is some radiation amount of heat also there. So I have just given a brief outlay of the flow of heat that is there in the system. So the endothermic reactions, they are heat source. So endothermic reaction are the electrochemical cell reaction and the water gas shift reaction. So the reforming reactions are rather endothermic reactions. They tend to balance the heat generated by other reactions. So just a slide showing the various flow of heat for different different type of heat, that is conduction, convection, and radiation, that is given by this particular slide. I am just rushing through because the time is going up. So this is the conduction, that is because conduction is mainly in the solid region of the fuel cell. So this is the planar SFC, the conduction. Then the convection that occurs from the solid region, which is at high temperature, to the channels, that is the flow channel and their channel, shown by blue. Shown in this particular red arrows here. So convection takes place in the flow channel, it takes place in the oxygen channel. Then the radiation heat transfer occurs. So radiation heat transfer occurs from, because it is at very high temperature. Normally we have temperature of 800 degrees centigrade. So radiation heat transfer has a role to play for that matter. So for that, radiation heat transfer occurs from the solid region to the channels, right? So if we come to the design of SFC, there are basically two designs. So one is the planar configuration and the tubular configuration, right? So tubular configuration has an advantage that it has a self-sealing mechanism. So a tube is there, we can feed the oxygen or the air to the center and hydrogen and the periphery. So there is a self-sealing mechanism for a tubular SFC. So planar SFC has an advantage that it has a higher power density. So at that we will just discuss in the next slide here. So this is the planar configuration. Just see, we have fuel fed to the fuel channel, that is the anode, and there is an electrolyte, then there is a cathode, and the air that is fed at the cathode, right? And of course that, but the reactions I have told that of course oxygen that changes into oxide ion, they migrate through the electrolyte, they react with the TPBs with the fuel, and it produces water. And it just shown in this slide is a cell repeat unit. There is an interconnect shown here. So this is one cell. So these different cells are connected with each other by means of some interconnecting material. So interconnecting material basically connects anode of one cell with the cathode of the another cell, right? So this is now a tubular SFC. So it is made in the form of a long tube with a porous wall, right? And there is a sandwich between, there is electrolyte that is sandwiched between two electrodes. And just see the stack of tubular SFCs that is there, right? And now a comparison between planar and tubular SFCs. Power generated is higher in planar SFCs. Ease of the fabrication is also higher in planar SFCs. Cost of fabrication, ease of fabrication is easier for planar SFCs, that is difficult for tubular SFCs, right? Cost of fabrication is higher for planar SFCs, it is lower for tubular SFCs. Sealing is better, easier in tubular SFCs, it is difficult in planar SFCs. So then long-term stability is also good in tubular SFCs, and thermocyclic stability is good for tubular SFCs, right? So design, I will not just go into detail about this. We have basically the three elements are there. One is the anode, cathode, and electrolyte. So we can have an anode supported SFC, an electrolyte supported SFC, and a cathode supported SFC. When I say supported SFC, that means the one which is thickest. So if there is an anode supported SFC, the anode will be the thickest. There will be an electrolyte layer and a cathode layer, right? So normally we use an anode supported SFC because we use a thin electrolyte, because thick is electrolyte, so it will lead to greater amount of resistance to ionic diffusion, right? So then these are the commercial SFC designs. One is the seaming Westinghouse tubular design. There is a segmental type tubular design is there, and a planar design of a Sulzer Hexus, that is referred to as BMW design, because it has been used as a battery replacement for BMW 7 series of cars, right? So this is the seeming Westinghouse tubular SFC design. So it is a tubular arrangement, but just see what is the arrangement is there. The air goes through the central channel, it transfers its direction in the central figure shown here. So it transfers its direction, it moves in the periphery, and then this is a basically on this side is the cathode, then center is electrode, and outside is the anode, and the fuel flows on the outside of the periphery of the S2FC, right? And just shown here, what is the electronic flow current pathway that is there for a seeming Westinghouse fuel cell SOFC. The different materials that are used, of course, lanthanum strontium magnetite is used as a cathode. YSZ yttrium stabilized zirconia as an electrolyte component. Anode is nickel on YSZ as a material, right? So this is seeming Westinghouse tubular SOFC that has been developed. It is in Pittsburgh in Pennsylvania, and it is the first SOFC that was built with coupled with the gas turbine system. It is a 220 kilowatt power plant, and it nearly has it converts 60% of the energy contained in the natural gas into electric power, right? So why seeming Westinghouse generated and tubular SOFC? Because one thing was it has a self-sealing mechanism, so thermal mismatch was avoided. Of course, there is a drawback of that. There is a long electric current pathway that has to pass through for the SOFC. For electric current that is flowing at a larger distance, of course, the amount of resistance will be more, and of course, some reduction in the voltage produced may also be there, right? So, to overcome this particular reason, seeming Westinghouse, they generated a tubular SOFC with high power density design. So high power density design, what it exactly had, there was ligaments that were present in the cathodic section. So the cathodic was flat, and ligaments were present. So these ligaments that were present, they tend to decrease the ohmic resistance. So they are basically flattening out this SOFC, basically tend to decrease the path of the electrons for completing the circuit, right? And so that is the advantage, and that is the main thing. I will not go to the next slide now. So another design, that is a planar design by Sulzer Hexus. So some advantages are given, and they are given. It is easily stacked. It has no long current pathways. So it is easily, fabrication techniques are very easy. Screen printing and tape casting, typical techniques of fabrication have been employed. And some demerits are there. There is long-term stability, and it requires optimization of mechanical and electronics, electrochemical stability of the materials. So the materials are similar materials, somewhat similar materials that have been employed for the other SOFC. So fabrication techniques, the thicknesses, they are given here, right? So this is slide just shows the stacking of SOFCs. So we can have a flat plate design involving different plates connected with each other by means of interconnect. We can have a seamless tubular design. We can have a segmented cell in design, that is basically a tubular cell, but different segmented, they are fragmented together so as to decrease the ohmic resistance. And the latest design that is there is a monolithic design. So monolithic design is basically a new technology in which this, just see here the monolithic design here. So monolithic design is consists of this V-shaped curvatures in the plate. So of the fuel cell component. So that leads to pathways for passage of the air and the fuel through this SOFCs, right? So I will not go into detail about this. Then let's come to the applications of SOFCs. So the SFCs are used for power generation systems, right? So there are mainly three components for SFCs for power generation system. First thing is the fuel processor. So we feed a hydrocarbon fuel. So that hydrogen-rich gas, after fuel processing, that is fed to the SFC stack. That SFC stack generates water, and it produces DC electricity, the DC current that is fed to power conditioner, from which AC current that is withdrawn, right? So this is another modification of a simple electricity generated by fuel cell, that is CHP, that is SFC CHP, that is combined heat and power system. So in this, what has been done is that the waste heat from the fuel cell that has been used here in the afterburner, it is fed to the reformer and the preheater. So preheater can be used for preheating the fuel and air that is fed to the fuel cell, right? So that basically increases efficiency. The efficiency for a traditional fuel cell is 50%. So that this increases the efficiency up to 85% for that matter. So then we have one SFC with the gas turbine system. So in an SFC with gas turbine system, what we do, the gases that are leaving the fuel cell, they are fed to the combustion chamber in the afterburner. So these gases, when they are undergoes combustion, they are fed to a turbine and it drives the turbine, and turbine is used for generation of more amount of electricity. And so this is co-generation of SFC with a gas turbine system. It is referred to as SFC GT system. So now, as a chemical engineer, I just had some interest in this. Of course, not much research is done regarding this right now. But besides the production of electric power, so there is co-generation of chemicals also that is possible with certain fuel cell systems. So what is that exactly? So it consists of three components. One is a fuel cell, an external load that is there from which electricity is drawn, and the chemical product recovery unit is there. So one system involves the conversion of ammonia to nitric oxide, and the traditional materials are used are this. Second component that is used is the synthesis of hydrogen cyanide, that is acts like a fuel, and that is synthesized, and this synthesis gas that is produced, it is used as a feedstock for hydrocarbon and for methanol manufacture. It is also used for nylon synthesis, nylon 6 synthesis, right? So these are the various commercialized stationary power plants has been installed in a number of places. So I'm just going to detail about this particular slide. So if we want to have a distributed power generation system, that is, if I want to have SFC or fuel cell for my purpose, household would need. So for residential purpose, if I need a fuel cell, it will be just a small fuel cell that will be just the size of a deep freezer or a furnace, right? And just shown here, a small residential fuel cell is there. It costs around $5,000 to $10,000. So if I just see the cost analysis, this is some data that has been taken from USA, where this has been developed. So the charges about homemaker 20 cents per kilowatt hour of the electricity that is generated, right? So now let's come to transportation sector. So traditionally, it is the polymeric electron membrane cell fuel cells which are used for transportation sector, I told. So fuel cells can be used for clean diesels, for gasoline electric hybrids, for hydrogen internal combustion engines. It can be used for hydrogen fuel cell vehicles, right? So SFCs for transportation sector are advantageous because carbon monoxide can also be used along with hydrogen. So then higher operation temperature leads to onboard transformation of the hydrocarbon fuels. And further, no novel metal catalysts are required for SFCs for transportation sector, right? So this is a typical just a line diagram of how SFC can be used in motor vehicles. So hydrogen is fed to the fuel cell stack. So that is basically goes into a motor controller, which is connected to a battery, and so there is generation of power which is it can be used to recharge the battery, and it can give the power back. So this basically goes to a motor generator, a powertrain, and that basically produces the power for a motor vehicle, right? So Honda company that is looking at vision for making fuel cell vehicle. So this is the showing that traditionally it was internal combustion engines that were used. Now the technology has gone up for using hybrid system, that is hybrid fuel systems, that is hybrid electricity and fuel system. Then we have PHEVs, that is plug-in hybrid electric vehicles that are there. And fuel cell vehicles, that is zero emission technology that is being proposed for by Honda, right? So this is a typical design of a vehicle Honda has designed for using as a fuel cell. We have hydrogen tanks here, one at the back and one at the below the back seats. Then there is a battery here, there is a powertrain, and this is a motor, right? Then right now Japan is making great developments in the use of fuel cell technology. So they are making hydrogen easily available in commercial fuel hydrogen stations at different locations in metropolitans, right? And Honda has developed one smart hybrid station. So these are compact smart hybrid stations. Just see the small size of the smart hybrid station that is there that can be used for feeding hydrogen to these cars, right? So current initiatives, robust fuel cell that has been used by Nissan for using methane at intermediate practical temperatures for using in e-biofuel cell. So I will just show you one Toyota fuel cell vehicle design of a fuel cell. I think so that will be interesting. So just see this particular video, you will get to know how the fuel cell works in a car. So Toyota has developed this particular technology. वीडियो नहीं प्ले ऑडियो एक्चुअली मैं अपना कनेक्ट किया है ना एक्चुअल ऑडियो पे मैं चेक करा ऑडियो यूएसबी ऑडियो करा है ना हाँ बस कंक्लूड करना बस एक दो स्लाइड करना बस So again, there was some network issues. So I was just playing the video showing the recent design of the fuel cell vehicle that has been done by Toyota company. So just I will just give a recent news that came in Economic Times in on 25th July 2020, right? So at HFC, that is the database company that made a world record of the amount of hydrogen generated for computer backup power. They generated 10,500 kilowatt of electricity in 48 hours, zero carbon, reliable, grid-free power. Right. So if we just see present scenario of electricity that is there, 416 tetrawatts of electricity that is used globally. So out of which 3% of the electricity that is used for the use of this power data centers, right? And the data centers capacity that doubles every 3 years. So if we just they worked this for 48 hours, and in the 48 hours of operation, 815 kilograms of hydrogen was used, and 10,560 kilowatts of electricity was produced, which is enough amount of electricity that can provide electricity to an American home for a year. And the byproduct was only pure water. It was 7,240 liters of pure water. That is enough to supply water for an average a month. to a person in US, right? So hydrogen fuel cells, they can be used as UPS and providing backup power, and they are dual maintenance and maintenance free, so they are silent. No caustic pollution is there. So what are the barriers to the fuel technology is one, it should be made affordable. So I just gave you an idea about the cost of the residential fuel cell. So they should be made affordable, then durability should be there, the fuel supply should be there, then precious metals are used as catalyst, so that is the barrier rather. So we are still trading on the foreign dependence of other. How we are trading on foreign dependence of other? Rather than using petroleum as a fuel, what we are using natural gas as a fuel. So again, we are basically, if you're using natural gas for hydrogen as a fuel in the SOFCs, so basically we are still depending upon foreign dependency, right? So although fuel cells, they only emit water, so the internal forming of the fuel cell, they produces NOx that leads to smog. So hydrogen, when stored in cylinders, and abrupted leakage may lead to reduction in the global oxidation capacity, and increased troposphere ozone may be formed, and that may induce halogen or induced ozone losses that may be there. So what is required is the hydrogen economy. It needs support from some combination of increased renewable power, the revitalization of the nuclear power, and conservation to promote diversity. Right. So these are the factors that are towards the beginning of these barriers. So there have been widespread fuel cell vehicles been demonstrated in these two instances has been reported here. So fuel cells have been used for stationary power backup systems, and these are public-private partnerships that are there, that are developing alliances, and they are developing certain goals for generation of electricity through this pollution-free fuel cell systems. So SATA is one, that is solid state energy conversion alliance is there, Office of Fossil Fuels is there, National Energy Technology Laboratory is there, Fuel Cell and Hydrogen Energy Association is there. So these are the various associations that are dealing with fuel cells right now, that is weakening the barriers involved in fuel cell technology, right? So these are the references that has been used. Of course, there are some research work that is done by me. So these are my references. Of course, the first reference is the same. I published a chapter in the Material Science Forum that there is a book where a solid oxide fuel cell future source of power and heat generation chapter was there. That was there. Of course, I also did some recent research work on parametric sensitivity of a tubular SOFCs. So these are the various my publications related to this particular fuel cells only. And so thanks for patient hearing. Of course, the network was a big issue. Of course, there was a problem regarding the network, and again, I think so some interruption was there for that matter. I regret for that matter. Right. So any queries regarding that?